This is the EHRI NCS Module 8, focused on the second session of Informatics and Analytics. I'm Jessica Castner, the President and Principal of Castner Incorporated, and the Director of this program. Regardless of the analytics and data science and informatics skills you arrive into the workshop with, this module designed is where all you need is curiosity. We'll work through the rest together, and I think you'll find some of these tools very useful, regardless of your design. We are so grateful to the NIH and NIEHS for funding in order to conduct this workshop. Here's our funding statement. Let's take a moment to evaluate where we are in the whole workshop and how the content has been structured thus far. We've progressed where you've evaluated a theoretical model for your project, selected a research design, and considered variables and measures such as physiologic variables, biomarkers, and measures of exposure. In Module 7, you began to look into informatics and analytics, and here we continue that journey before we move into special populations. I just want to give a brief history on the 9 Bradford-Hill criteria to consider causal inference associations. These criteria were published in 1965 and continue to inform a lot of the logic behind deciding if a relationship is causal or an association. This is rather controversial in medicine in looking at observational data for causal inferences. Here, the RCT is the gold standard, particularly because a lot of science is based on FDA criteria for safe and effective pharmaceuticals and devices. The rigorous use of observational evidence is still controversial in medicine for intervention evaluations. However, causal inference from observational data and natural experience are a long-standing foundation of the science with maturity in environmental health use. There's really many times when it's not ethical to expose a human in a controlled trial to some of the environmental toxins or pollutants of study. Please do note these Bradford-Hill criteria listed on the left are currently informing the Cochrane grade system to evaluate the overall quality of a body of evidence. There's a hallmark paper in 2011 by Holger Schunemann, and it's still in the current grade book. It was directly used in the 2015 Environmental Protection Agency Integrated Science Assessment Preamble. These are systematic reviews used to evaluate evidence criteria related to criteria air pollutants and regulatory standard setting. The bold criteria were used in the 2019 National Toxicology Program OHAT evaluations, another systematic review. So these 1965 criteria continue to be incredibly relevant. What are the criteria? First, look at the strength of the association. Large, precise, small confidence interval statistical estimates or a large magnitude of effect increases the confidence in the association. I know in a lot of my work when we're looking at outdoor environmental exposures of pollutants compared to indoor smoking, the magnitude of effect of that indoor smoking exposure absolutely overwhelms due to the strength of the association, the precision, and the magnitude of the effect in our statistical modeling. The second criteria is consistency. We know this is reproducibility. Is it the result reproducible across several independent studies, or are they discordant? If you're finding discordant results, can they be explained by dose difference, confounding, or a power issue that can actually get smoothed out with low levels of heterogeneity in a meta-analysis? Specificity is the third criteria. Does the evidence link the exposure to a very specific health outcome? Consider the specificity of chemical weapons like chlorine and pulmonary edema, or nerve agent and the neuromuscular paralysis of the diaphragm. Outside of these high-dose, perhaps weaponized agents, most human health outcomes have multiple holistic social, behavioral, and biological causes in environmental health research. Temporality is the next criteria. You want to be very careful to design to observe a temporal sequence between the exposure and the effect. Cross-sectional studies, like we learned in the last module, are largely descriptive in nature, but studies designed to look at causation and causal inference consider the timing of exposure and the subsequent health outcome. While again, these population representative descriptive studies are absolutely key to informing policy interventions, temporality may be a very important growth area for nursing science and environmental health. Be careful when you're looking at the cross-sectional design. It tends to be very economical and very important, but it limits causality inferences. The next criteria is dose response or biological gradient. Increasing the health effects associated with a greater exposure are observed, right? You'll want to consider in this the peak exposure and the duration of exposure. Are we talking about chronic exposure as the dose, or are we talking about a single high dose exposure? The next criteria is biological plausibility. This is a proposed mechanistic pathway based on experimental evidence that links that exposure to the specific health effect. Even if you're working in ecological studies, population epidemiology, it's important to have this knowledge in your theoretical framework, in your literature review, in the discussion. Several of the informatics tools that are broadly applicable to everyone in this workshop address getting information and developing your argument about biological plausibility. Coherence is the next set of criteria. Do different lines of evidence between molecular test tube studies, mechanistic studies, population epidemiology, controlled human trials, animal studies if they're conducted, or ecological studies point to and support a cause and effect interpretation, or does it introduce uncertainty with different lines of evidence? Consider the coherence across fields and disciplines, across different study designs, and health outcomes in your literature review. Next, we have experimental evidence, which is strong evidence for causality is provided either through natural experiments or through controlled trials. When a change in exposure is found to result in a change in the occurrence or frequency of that health effect, we have experimental evidence. Last, and one of the criteria that has tended to fall off of modern interpretation is analogy. That is, can we find within this class of chemical we're looking at, or this type of exposure, maybe it's a thermal extreme, an established structure, an established pathway with an analog, right? Is there a known mechanism of action from something similar that then this has a consistency across exposures or within a class of exposures? Because in the 60s, this may have been relatively new, and now with our informatics tools, it's so well documented. Analogy can be found for many things, and so that last criteria sometimes is not well addressed. Why are we looking at DAGs as we step into this section? You know, holistic and contextual research relationships are rarely linear in nursing. We also need to consider the mixture of exposures, whether they be social, physical, and outcomes, and how they influence one another. For causal inference of observational data, consider which variables must we control for to draw causal inference, what relationships can be inferred, and perhaps if we need to be economical and limit our variables and measures, which ones aren't going to influence that causal inference. When might additional statistical controls actually worsen the causal inference and reduce our power unnecessarily? Can you guide and clarify theoretical reasoning in data collection and variables in a DAG? And I'm going to get a little statistical here, even though it's a concept map, right? You're setting up the opportunity to test a non-parametric structural equation modeling. So if you're familiar with SEM, a lot of the terminology will look a bit familiar. However, you develop this concept map by using content expertise, theory, literature review, and evidence from your own preliminary studies. This can be really important when you might be looking at the wrong estimation theory. It might misspecify. Likewise, these may not be linear relationships, or their interactions might be a better fit for a more structural equation model. Regardless, even if you're not going to do a quantitative test, this is very helpful for your own, if you're developing your own theoretical model, to clarify fuzzy concepts and relationships in your thinking as a researcher. A DAG is a concept map graph with variables as nodes and connections. They are directed because you are specifying the direction of the connection in the relationship in this causal inference pathway. You emphasize an exposure and a health outcome in this complex mixture relationship. You can look at direct and indirect relationships. They can be graphed with intermediate outcomes. They must be acyclical. There's no circles, no closed feedback loops, and no looping back is allowed. Why? This strengthens the causal inference pathway by considering the temporal relationship. If A, then B, then A again, you have to draw it as A at time 1, then B, then A at time 2. So again, you are drawing it with temporal considerations, strengthening the causal inference. Let's look a bit about the uses. It's often used for mixtures, pathways, and interactions with separate individual effects. If you know that there are confounders, mediators, or what we call colliders, we'll discuss this complexity. This can often be used. However, you're specifying the direction of the relationship, which means that might be an area of uncertainty or misspecification. Missing variables in relationships introduce misspecification. You need to be very careful about correlation versus causation and make sure that this is temporal, that your outcome comes after your exposure. And again, no closed loops. There's some packages, and we're going to look at DAGD in our real-term workshop. So here we look at the simplest form of the DAG, exposure, outcome. In number 1, we have a direct pathway. Let's consider chlorine gas exposure and eye irritation as our outcome. In number 2, we have an indirect pathway and no other path between exposure and outcome. Perhaps here we would say chlorine gas exposure causes acidification of tears in the aqueous humor of the eye, which is what causes the eye irritation. We see a complete indirect causal path between the exposure and the outcome. Now let's just consider number 3. Here we have a mediator. Here, perhaps we'll consider chlorine gas exposure causes contact lens damage as mediator 1 and eye irritation both directly and indirectly through contact lens damage. Note that relationship is a mediator. This is an important indirect pathway to consider in causal DAGs. The exposure case causes the health outcome directly, and the exposure causes the health outcome through the mediator. We'll revisit this and other important pathways to consider in a moment. But first, we know the path from exposure to outcome is rarely that simple. Here's an example from the published literature on the exposure of chronic traffic-related PM2.5, ozone, and nitrogen dioxide with the outcome of ischemic heart disease, labeled as IHD. Note each of the pollutants are conceptualized with additional indirect and direct pathways of influence, such as an ancestor of socioeconomic status, smoking, age, gender, diabetes, and a green buffer from major traffic roadways in that built environment. We will replicate this DAG at our workshop, focusing on ozone as the main exposure variable. You will be provided with an optional demonstration pre-recorded here if you want to practice ahead of time and begin to apply this technique to your own project deliverable. When we replicate this model in DAGD software, we gain additional insights into the variables that bias our causal inference between ozone and the main traffic-related exposure and ischemic heart disease. Biasing pathways are depicted in red here, where causal pathways between ozone and IHD are in green. Note how nitrogen dioxide in this model. It is very important as we consider how we are adjusting for biasing pathways of moderators to draw causal conclusions. I would also, in my community, want to give this some deep thinking if this arrow is directed in the correct way and if it shouldn't be from NO2 to ozone. DAGD includes a tool to consider if we condition on SES. If we condition either by controlling for it, adjusting for it, or perhaps only sampling from a strata of SES. We ensure that we measure and adjust for it. We've closed a backdoor path and increase our confidence we are modeling a causal pathway. If our relationships and assumptions are correctly directed in this directed acyclical graph, if they are correct. So we see here in green, We have our causal pathways, and we do not have any red biasing pathways once we condition on SES. Let's explore two other very important variable types in DAGs. The first is a confounder, where the variable causes both the exposure and the outcome. When creating a DAG, we consider, what if A causes both the exposure and the health effect? For example, the path between lead exposure and developmental delay. Perhaps living in a low-income neighborhood is related to both the higher incidence of lead exposure and other causes of developmental delay. A collider, on the other hand, is a variable where two or more variables cause this collider. Two or more arrows point into this variable. If the DAG terminates in the collider, we generally don't have to adjust for or condition on this variable. We simply have conceptual clarity. If we need to be parsimonious and limit the number of variables we collect or model in the causal pathway, this might be one we consider not measuring. However, it does bring up an important consideration about association and not causation. Here we revisit colliders on the top, confounders on the right, and mediators on the bottom to strengthen the clarity and present in another graphical form for you. Let's focus here on colliders. We often consider correlation or causation. What are we thinking about in our DAG, as our focus is causation? When you model a collider, consider the associations or the correlations between the two variables that independently cause the collider. And consider if an ancestor should be modeled here, right? An associated variable. One sort of lay example is the grass is wet as the outcome. It could be from the sprinkler or it could be from the rain. They're correlated because I might be more likely to turn on the sprinkler if it isn't raining, but I don't have an automated system where rainfall consistently determines if my sprinkler gets turned on or not. They are not causal in this instance, but they are associated, they are correlated. Here you see age does not directly cause frailty. However, frailty is correlated. It's more likely to occur as we age. They're not causal unless they're colliders. You might want to think about how you annotate this or as correlation or association, not causation, in your literature review to inform your DAG and to think deeply. Here is a more recent and complex path model in green, biasing paths in red, and then ancestors or things that come before outcomes and exposures are well depicted. This is the relationship between anti-androgen receptor activity and infant cryptorchidism. So again, this is or undescended testes in male infants. Here it investigates the effects of potential toxins in breast milk. Let's just take a moment and examine our collider further. Let's imagine we're building this DAG, and the only variable we've included so far are on the left-hand side, antibiotics, smoking, and maternal toxicant. Note that maternal toxicant would then be a collider for antibiotics and smoking, making us think about how antibiotics and smoking are correlated, but not causal in this diagram yet. We might want to give some additional thought to this, as smoking is a causal factor in higher risk for infection and the subsequent need for some antibiotics. Some, not all. Perhaps this model should be extended with an infection risk pathway. Identifying colliders can be very helpful to clarify this kind of causal or association thinking. We also see that this model includes multiple biasing or pink paths that limit our confidence about the causal relationship between the exposure and the outcome. This means there's additional variables that need to be controlled for, adjusted, or conditioned upon to strengthen the causal inference modeled here that we would want to explore further. As you construct your DAGs, consider how you are strengthening causality with the Bradford-Hill criteria and the Bradford-Hill criteria descendants. In particular, we talked here about temporality, specificity, for example, how many pathways should be considered in causing any outcome, and biological plausibility. They're important to consider each step. We gave a rapid overview in the introduction of causality criteria, and especially causal inference from observational studies and DAG uses, common misspecifications, pathways, and key variable types.